Okay. So, good afternoon. We are going to talk about advanced OpenMP. I hope you attend the Daniel class to talk about introduction to OpenMP. So this is the second part of the same topic. Okay, overview of today's talk. First, I talk about parallel control structure, which is OpenMP parallel. Later, I will talk more about work sharing constructs, which are two four, OMP4, and OMP action. And then we talk about data environments such as private, shared, first private, last private, and so on. Also discuss runtime functions such as OMP get num threads, OMP set num threads, OMP thread, and scheduling policy. At the end, I will mention some example MPI and OpenMP programs, as well as few information about OpenMP 4.0 features. So I think as you OpenMP team, which consists of master workers. And the region is a block of code executed by all threads. So use the parallel region. Then after you may some directives such as OMP4 or do options, and then whole that code segment is going to be executed by multiple threads. Parallel region can be nested, and you can use the if clause to apply on parallel region, like whether you really want to execute this parallel region on this condition or not. And sharing constructs which are going to be the part of parallel region, and the loop section and so on. So OpenMP directive parallel constructs. So in C++ it looks like Pragma and directory name, names and the process. About process in coming sections. Uses $and OMP directive name. In 190 you say $OMP directive names. So the example of or the syntax for parallel region. So it says pragma OMP parallel, and then you can have the private and the list of variables, shared list of variables, default, first private, reduction, copy in. So the structure, this is the fundamental of parallel construct. So how in C++ it looks like? In C++ you have you can mention like that OMP parallel, and then you have structure block. And program use similar to C++, you can have $OMP parallel, and then you enter parallel region. So parallel directives, it is the team of threads, and become master of that team. While all directives, they don't create any thread. And first thread, that is going to be the thread number 0, called master of that thing. And then after it enters into the parallel region, and then the code is going to be duplicated, and all threads are going to execute the same code or same code segment. There at the end of parallel section, so once you quit the parallel section, all thread has to has to wait to finish to complete the task, and then after that is going to be the implied value. There is barrier in the parallel directive, and uh, and only can continue execution beyond this point, not all other steps. So once you close the parallel directive, only going to execute the rest of code, and that is the master. So Daniel slide here is the OpenMP constructs. These are the core elements of OpenMP. So we talk about the parallel control structure, which is the parallel directive, and now we got work sharing, which is do parallel do in section. Requirements like the first private, shared, and synchronizations like critical, atomic, barrier, single, and some of the runtime functions. So you can set how many threads you want to use for this particular parallel instance or for this parallel section. So let's talk about the work sharing construct. So in the work sharing construct, it divides the code among the number of threads. And as I mentioned before, it must be enclosed in the parallel region. So you can have like OMP parallel 4, or you can have OMP parallel and then OMP 4. So in the parallel region, this work sharing construct, they do not launch or create new threads. They just execute the threads created by the parallel construct. So you have number of threads in the parallel region, and then work sharing construct will use those threads and run the code. Yeah, and there is no implied barrier to enter into the work sharing construct. So any thread can enter into that work construct or directive anytime. Always the implicit barrier at the end of work sharing construct. So if one doing the work, or rest of the thread has to. And the work sharing construct in C++ and Fortran. In C++, for the distributed iteration over the thread, you have pragma 4. In Fortran, you have OMP2. Distributed dependent work unit, which is similar to, you can call it as a task level parallelism. You can have multiple sections, and you can multiple threads can execute each section simultaneously. That you have pragma OMP section. In Fortran, it's the OMP section, and you need only one thread execute a given code. You know, pragma OMP single in C++ and OMP single in Fortran. And there is also this parallelized array which you use using the OMP work share. So when you want to have like let's say array of A, and then you want to have a combination of array B and array C, you can OMP work share and to do that. Enabling Fortran. So construct in the visual way. So if you look at do or for, you see like one master thread, and then it has multiple the team of threads which does do the work, and then it joins. That thread will continue and execute the rest of the code. There is to have the different types of tasks, and some take more time than others. So that's in the second is where you see some some are bigger than others because some takes more time than others. Only one thread is going to execute the task. All threads are going to be idle, and then at the end, and the master thread will continue. So here directives like for Fortran, OMP2, schedules. I will talk about schedules. There are different types of schedules available, which is based on your requirements and and just you can choose different policies like dynamic guide and runtime. And the work sharing constructs four directives for C++, pragmatically for you see the similar arguments like the schedule, order, private, first private, and so on. So there is this work sharing construct called section. So section is, it reminds me the like the task where you task and you assign different tasks to different threads. It may they may need to access a different way. While in the for or do in Fortran, each thread will execute data. While in action, it may possible you are executing one function by one thread and you are executing another function by thread number 2. So, and the important thing here is it may possible the load imbalancing because some thread need to do more work than others. So, so you need to be careful about how you do the load balancing when you have this type of frag in your code. And here is an for C, like OpenMP parallel, and within that you have OpenMP section, MP section, where for it is going to use call function 1, maybe just calculating the max. The another thread will execute the function 2 to calculate minimum or something. So the basic how to write the section, how to write the task level parallelism in OpenMP using directives. And here is the single construct. So the construct, one thread is going to only one thread is going to do the task to the work. All other threads are going to be remain idle. And the thread chosen could vary from one run to another. That means it may be right now. Means for the first run, thread 0 is going to do the work. In the second run, thread 5 is going to do the work. Executing in the directives wait and the directives unless no wait is specified. That means where in the directives all thread has to wait until it is going to finish its work. But you can say no wait, and that all other thread are going to do something else. And here is an example how you use the pragma single. So let's say pragma MP parallel shared B and the private I. They just execute this a equal to 10 printf single construct executed by thread only by thread. You only printf one time and automatically have the barrier. So all is going to wait because I haven't specified the no wait here. And then after the next thing is pragma MP4. So this code is going to be executed by multiple threads. Code segment that pragma MP single bracket going to run that. While in pragma 4, multiple thread will execute those that part. So let's talk about data environment. So then types of available. How do you want to share your data, or do you want to make it private first, or do you want to make it first private or last private? So the default behavior is that all variables are shared except the big. That is behavior. All variables are shared by all the so that means you can write the same memory location for each variable. It's okay until that multiple threads are going to write for that variable. In that case, you will have the different value for for the same variable in different for different threads. So index is private, so each thread has its own copy of that. So now about here, to share and type. So as you, the top is the Fortran code and the bottom is the C code. I first equal to 10 and 1 to I max. I2 is by I, and 0 5 equal to I first plus I2, and finish the loop. So variables are shared by default, right? So that means I2 is shared, I loop index, so that is value, and I also shared, right? But as you said, we are taking the value of I2, and we are taking the I first and putting 0 of I, right? So this is I first plus I2 value. So in that, when updating the value of I2, each thread needs to have its own copy to variable, and that's what I2. In case it will give you the correct answer. If you don't specify the private I2, then you will have the incorrect results for J array. So now let's get back this what happened. So the before and after the parallel code statement. So here in the before I first equal to 10 and 2 threads, we don't know the value, and then after when it spawns the additional thread, you will have I first, which is by default, so each will have the value of I first, but now each thread has its own I2 copy, so that I say I2 thread 0, I2 thread 1. So it is the same thread value I first, and they have their own private copies of I first. So you say thread 0, it has I equal to 10, and thread 0, it has its own copy of, and one can access I first, and it has its own copy of I first. So now, with this loop and the parallel region is the data dependency. If the dependency in your code, then it's hard to parallel. And I have example in cases it's hard to parallel. So data on one thread can be dependent on data on another thread, then it's the time is similar to the serial execution. And thread has to wait for another thread. So here is all of Fibonacci. So the code of Fibonacci looks like A of 1 equal to 0, A of 2 equal to 1, and then iterate. I want to know the first 100 Fibonacci sequences. So and do I equal to 3 to 100. A of I minus 1 plus A of I minus 2. Here the A of I equal to A of I minus 1 plus A of I minus 2, right? So the current value depends on the previous value and that value. Here, parallelize that code, and let's say I have the from 1 to 100. Execute on 2 threads. The thread 0 gets 3 to 51 and 50 to 200. But when thread 1 needs to calculate 52, it needs of 51 and 50, right? So A of 52, unless it sets a value of 50, 1 and 2. So serial processing, because once thread 0 finish all the values, you can start going from 52 to 1. So we do for the dependency, like a serial loop, you can execute that serial loop in the reverse order and get the same answer. Then it's easy to data dependency in the loop body, and that way it's so look at the another scenario where I want to call this function 100 times on different. So here is my calculation ix and y, and index loop, so that is private by each thread. But here is if each call write x and y value to the disk, then it will problem. So if and y value needs to be written on the disk, then x and y has to be right. If it, then if possible, two threads are going to write different values for it on the memory and will overwrite another value. So what if you can make it private? You can hundreds of x and y values and then merge that. So basically, this relation. You can, or let's say you want to have the summation of 1 to 10,000, and you can divide into chunks of, let's say, you get a summation of 500 chunks, and then again do the reduce operation and those results. Okay, so run. You can make private as a default rather than share as a default. So I meant for like default everything is shared Excel looping. But in you can make everything private by default. So it needs more memory because each thread now has own data, right? So it's more memory, but also helpful sometimes when you see some type of incorrect result. You can private and make sure each thread has its own memory and write it and get the correct result. So here is how you can make the private. So OMP parallel to and continue OMP default and say private. So private. In the shared form, you need to say shared I time x and other variables. Okay, and you can use default to none. That means you have to whatever the variables you have to specify whether it's shared or private. So it doesn't assume anything in this. Now it's up to user whatever you want. Like if you want to make it some variable private and shared, now you have to use that shared and private directives and put in your code. Like default is none, and can have shared in the private code. So now let's talk about the first private. Why we need to use the first private? So suppose we need a running index, total each index value on each set, right? So here equal to 0 and I equal to 0 to I max 1. I need the I for value for each set, right? But the unfortunate is if I were declared private, the initial value would not carry out. For let's say in case the price wiper is private, I cannot value 0 in the loop, but value 0 into my loop. So in this scenario, I have to make it first private. So when private, that means if the value are equal to 0 when it starts executing this body. So hence the behavior of private clause plus automatic initialization of the value. So the first private, whenever you use some values outside the loop, in out from the loop to the inside of the loop, you make it first private. And the thing here is called the last private. So when you leave the last value of the execution after, then you have it. So here is the value of the last index. Then I make the last private I. That will have the value of I after the loop. Now let's. So this is a feature in OpenMP which is called reduction. So as you like sum equal to 0.0, and I want to have the summation of the array of 100 values. Let's say the simple code. Let's say this is the serial code for I equal to 0, I plus I plus plus, and I want summation, right? Can I experiment just by just going to parallel 4 on top of 4? I cannot easily, because as I mentioned, if each thread is going to write the same value on that variable, then you will not have the correct result at the end of the loop. For reduction clause, where implicitly what it's going to do, it's going to create the copy of some variable. So each tab will have its own sum variable. Once it's done, it's going to do the reduce operation on that sum of on the sum variable. Then we'll have the correct results of sum. So say reduction, and here is the summation operation, plus, and then you
could have you put reduction and then time. And at the end,
rather than having sum, you want to have multiplication or something.
Right. Like in this case, this we're exactly the same except for we have an asterisk.
Right. Right.
Instead of the plus sign.
Yes.
Then each thread would sum the and they would be black.
Correct. Yes. Yeah. So here are some of the operators which are available. So like you can have max, min, in, I or e, and or and not equivalent. In C++, the plus multiplication, minus, division, and or, and so on. Complement. So one of the most important things here to remember, the round of error, it may be different, right? Because now we're summing of all these 100 values into one value. So you're making some round of error. And private before each list variable is created for each thread. And reduction, the reduction variable is applied to all private copies of the shareable, and then it's finally the result of the variable. And I already mentioned about this OpenMP functions, but this is just there are some function which you can use to the number of threads or set the number of threads or their thread number. So now the scheduling policy, because these policies are important to improve the performance of your code. It's based on your code and how much it takes to finish the task. You need to change the policy. So there are 4 types of scheduling: stack, guide, and the runtime. Generally, runtime uh, policy needs to be you want to do some type of experiment. Which one is the best? So specify this. So you say OM4 and then you specify the schedule. In the bracket you say which kind of schedule you want, static, dynamic, and you specify the chunk size. An example, when I say chunk size means when you have instruction from 1 to 100 and you equal to 5, that means each thread will execute the the first the thread. You can say chunk size 100, that means only one thread will execute that thread. There is syntax like schedule, then you can have the time and then chunk size. Specify the chunk size, then the relation space is divided equally into the equal chunks. Specify the chunk size, then chunk size are simply to each thread. So here is an example. Let's say you have 1 to 46, and then you have small 4 threads. So in top list P0, T1, P2, and P3. So it's 46 into 46 divided by 4, and whatever the chunk size is going to do that much amount of work. That is the schedule set, right? Default. Now chunk size, let's say schedule static 4. That means you 40 divided by 4 for what is the cyclic fashion. So first finish 1 to 4. First is going to finish 1 to 4. Second thread is going to finish 1 to 4. Third thread is going to finish 1 to 4. Fourth is going to finish 1 to 4. Sorry, third is going to finish 1 to 4. Second is going to finish 5 to. Third thread will finish 8 to 12. Fourth is going to finish 9 to 16. Or 9 to 13. Whatever. 4 different. So you make the difference when you specify the time. Now dynamic schedule will divide the chunk size way. So you have this of work, let's say 1 to 100, and what thread finishes the work first, we assign the next work to that schedule. Here in the static we assume each thread is going to take the same amount of time to finish the work. But the case for all requirements. So in the dynamic, we are if one thread finishes the task much faster than the other, that we will get the other task. And so in the guide, it's similar to dynamic, where chunk start except that the chunk start with the large amount of work, and then it gets more exponential. Here it gives you a better idea of what's the difference. So when I say schedule dynamic C and schedule guided C, that's how it works. So for the dynamic, so let's say it is finishing the task, is finishing the first chunk, T1, T2, and T3, so on. So as like T2 and T3 are repeating more than T0 because those threads are faster than T0. T2 and T3, right? Showing voltage and T0. What is set in the 6? You say T0, 1, 2, 3, 0, 1, 2, 3. Because assume each thread takes the same amount of time. But here it's not the case. That's why you see more T2, T3 than T0. It first gets the bigger chunk. So that's why T0 takes more time because it's going to process. And it's going to be smaller and smaller. So if you set the T0, it's going to be much faster to finish that task than the first task. and then schedule. So the previously mentioned schedule, you have to define at the count time. And this one, you can defer it until the runtime. So you, in your code, you say OMP schedule guided or schedule dynamic. So which better depends. The static schedule is based for balance loop because list over. Each thread knows which task needs to be finished and it override that way. And smooth balance. The thing, it is used to have widely varying loads. Some takes more time than others. Then you think about using the dynamic schedule. But here the problem with the data locality because now you have this array which you are operating on, and then some threads are running on another socket, some threads are running on some other socket. Then it needs the memory, and it may have some performance issue. So it is less sensitive than dynamic because it is more time to finish, but then after it gets smaller and smaller. But when the first iteration takes more time than others, because allocate more work to do in the first iteration, and first iteration is already taking more time than others. And the runtime for some experimental purpose. So about the performance means I have known the topics which are the ways for the poor performance, like sequence forward, communication, data affinity, imbalance, and synchronization. Many of you already know about Engel's law now, and it says parallel code is more than faster than parts which can only be executed in serial. So more code which are in serial than parallel, then that much speed. Because if your serial code is going by only one thread or one core, then you won't see the performance improvement. Because let's say example you have the 100 lines of code, and out that only 20 are in parallel, which take 20% of time. You still see, you do not see the improvement in your performance because still 80% of time are going to be spent in serial code. All the code outside of the parallel region are serial. And whatever the code you put in master, single, or critical directives, all are sequential code. So this code should be as small as possible. That means you need to have more code into parallel region. Otherwise, it's not to improve the performance of the code. Another thing is the communication. So OpenMP, they use the shared memory, and by default everything is shared. So you see more and more variables are being accessed by different steps. And when you have the memory, it costs you the cycle. So cycle of main memory access, that is equal to 1 to 3 cycles of clock. So if you are adding some memory, it is similar to doing some computation on some mathematical computation on the CPU. Message pass, here is the communication spreading throughout the program because this thread is accessing the variable X, this is accessing the variable X, the thread is accessing the variable X. So you see all threads are accessing the same variable, right? You don't know because it's implicit. MPI, you explicitly specify I want to have variable X. So you are accessing that variable. easy to analyze the code in terms of communication because you know this MP rank 0 is accessing this variable. While OpenMP, it's hard to analyze the code. It's already human. The another thing is caches and coherence. So the shared value at given time, right? So you have an X, and let's say now it's value is 50. So accessing that value, it has it changed. If one thread is changing that value, it has to all other caches. I have a really good example of it. So here you see like L1, L2 caches, and each processor has its own L1 and L2 caches, and we have the shared memory RAM, which is this. Let's so here let's say I can exist one of the state, one called execute state, another one called read only, and the third called invalid. So in the state means that is you have the only valid copy which is correct. In the reading you have the valid copy, but it may be of another cache. And invalid means it is out of that use. So let's go here. The process from left side something, right, on the memory. Now the second left side is reading. So the video because it's fixed and it's no it's correct. The second one is it's read and it's no it's correct value. Now let's say the processor 3 wants to write that one, write that value, right? Now processor 1 wants to read it, the correct value of it, but 2 is correct value because what the processor 1 draw read that value. Processor 3 overwriting that one, processor 2 doesn't know, right? That means you have to propagate these values everywhere, and to update that value, to update all the caches, it's costly. So redundancy is important, but it is also costly. So these are simple cache pools and use the data. It means when you have near processor, you have to use you can. So one array, let's say an example, you have an array of 1,000 values. Whatever you operation want on that array, rather than fetching another array and then after fetching the same array again, because you are reducing the memory access and you are improving the data affinity as well. So write this subset large contiguous chunk of data, and then also avoid the false flag and other problems. And it is all like in the GPU programming, like what data you have in GPU memory, try to use that data and do the operation as much as you can before sending back to the GPU memory. Otherwise, you fetch it back from GPU memory. So the similar kind of concept. Okay. And so the first, first you grab private I and you iterate from one j equal 1 to n and equal to 1 to n. So first looks like this data affinity. The first, second, third, and fourth. Great. And each will have quality here, so it's easy to access those ones. And it was the cache means for cache. The second one, you see I say schedule status 16. I j equal to 1 to n and I equal to 1 to j. That means it's a triangle. It's not the square, right? So when I say 16, that means when each thread will have access to it, and until the 16 chunks, it is fine. But after that, it may have the cache misses. That data are not located next to each other. It's not contiguous. You need it from another thread's memory, another thread. Okay, so the local main memory is important, and it has no support for it. You have to manage how you want to store data and access the data. And the data is placed on the first processor, and one more thing, which is process policy. So when you use interstate, you test the memory. In that way, they will have the data reception near to its processor. And it can be from the communication and the computation. You have to express that different policies, and it will become a server because when coding may not know which policies to do. But once after you can easily get out static robots, better use case, and dynamic robots, better use case. Yeah, appropriate, then you can write your own scheduling algorithm. Okay, now synchronization. So very really expensive because when you have the barrier, that means it has to wait until their work. And of synchronization directives are available. So you synchronize all threads in the team. It will reach the thread will at that point, and all other threads have reached that barrier. There is, which is so then only specified region is going to be executed by the master thread. All other threads will be idle in that case. And it is kind of synchronization directive. It is also similar to the single construct. In the single construct, any thread can execute that part, but after that means the master thread can execute that part, which is so when you have some code you want to be by only one thread, then specify the like you want to do summation, then making it reduction operation, you say critical, and then you do the summation. Then all threads will come before that, and one by one will go to execute the critical action. This is called atomic, which is the mini critical directives. This ensures that the specific memory location must be updated automatically. So I think I have too much light on the performance tuning, but when you like, oh, my code is giving me poor speed of what I can do, we will classify whether it's a problem with the communication, synchronization, load balancing, or you can use profiler tools like total view, DDT, or tau in figuring out spend more time. Where is the problem? we go through this one, which is like the topic of hybrid MPI OpenMP kind of programming, how you can do the MPI OpenMP. So MPI is like multiprocessor, multi-nodes programming API, while the OpenMP is a single vector kind of functionality. So, but in the modern cluster, you see the multiple nodes and each node with multiple processors. So we use OpenMP board to maximize the use of that resources. And as you the prawns of MPI are prawns of OpenMP, and similar cons of MPI are prawns of OpenMP. So OpenMP MPI for portable distributed share memory can scale beyond one node. OpenMP cannot scale beyond one node, but if you combine both of these, then really helpful. You can scale your code. The MPI, it has the high latency and low bandwidth. In this case, OpenMP is useful because it has low latency and high bandwidth. So that's why what you can do, you can introduce MPI into OpenMP and scale it. You can put MP into MPI application, and you can use the communication of it. And in this, you can improve the performance and scale. So here is the pseudo code for MPI OpenMP kind of application. Just call the OpenMP function like init, frame, size, and do some computation. And then you send that results to the different frames, right? And once each has the results, they can do more work. They can use OpenMP threads within the single node, do the computation, merge results, and to the other MPI. I think here is the C hybrid code. It's similar to code. Mentioned in the OpenMP 4.0, there are some nice features available. One of the most important thing I like, which is the support for compute devices. So you can specify whether it's a GPU device or Intel Xeon 3 device, and execute the code on using the OpenMP 4.0. The SMT concept, which is similar to like the single data kind of thing, where you have the code, but you have multiple data, and you have that. So you are using OpenMP 4, you can use SCI concept. The task enhancement is also important in OpenMP 4.0 because you can group the task and also do the synchronization of tasks using the task dependency. So it gets the task dependency and it implicitly does the task synchronization. And when you do the synchronization, you have to do it affinity. In OpenMP 4.0, it has some functions like procbind or the environmental variable called OpenMP procbind, and you can do your threads to the particular. So in that way, it's not going to migrate one core to another core. That's all for today. Now, if you have any questions, feel free to ask.